and the space industry has begun to take full advantage of the capabilities and opportunities harnessing AI enables. AI can be defined as a theory and development of computer systems able to perform tasks normally requiring human intelligence or intervention.
Here at UEL, we create unmanned exploration solutions for missions in extreme environments, most notably for space exploration to the Moon and Mars. Our development portfolio include this Mars Ingenuity helicopter prototype that was flown in the Australian desert on a contract with NASA.
We adapt natural language processing and text mining methods to the field of space systems to accelerate the design of space missions. I also develop knowledge graph solutions to merge unstructured data and extract new insight with autonomous reasoning.
See here behind me is our spacecraft robotics simulator, a state-of-the-art facility in which we test autonomy algorithms that will be flown on board spacecraft. We have designed these floating robots to have onboard computation to run any state-of-the-art autonomy algorithm that uses machine learning.
Intelligent satellite swarms that can tag in and out, adjusting their orbit and focus to achieve a mission rather than a singular user-defined task. Or automated docking and refueling processes that would make an F1 crew look clumsy. And should I even mention the Lunar rover that our institute is aiming to help the Australian Space Agency build to do our part for the Artemis Accords?
Everyone, good afternoon, everyone. Thank you for joining us today. Our names are Matteo Capella and Priyanka Rajkakati. We are members of the IAF NextGen Plenary Steering Committee. For the past year, ourselves and our team members, Mariam Nassim and Dania Shepard, have been working to put together this excellent panel of young professionals and students that will cover topics of AI, artificial intelligence in space. These panelists have passed a rigorous application process and have spent months preparing to be here on stage. For this, as part of the organizing team, we would like to thank the IAF Workforce Development and Young Professional Program Committee, the IAF Space Education and Outreach Committee, Scott Medry and Carol Calnet for having supported us in preparing the panelists to be on stage today, and as well Kat Robinson and SJC, and all the others that have been helping putting this together, advertising it, preparing it, reviewing the application process. I will now leave the floor to my colleague Priyanka.
Thank you, Matteo. I would love to introduce our wonderful moderator, Professor Daniel Wood. Professor Daniel Wood serves as an assistant professor in media arts and science and holds a joint appointment in the Department of Aeronautics and Astronautics at the Massachusetts Institute of Technology. Within the MIT Media Lab, Professor Wood leads the Space-Enabled Research Group, which seeks to advance justice in Earth's complex systems using designs enabled by space. In her research, Professor Wood applies these skills to design innovative systems that harness space technology to address development challenges around the world. Prior to serving as faculty at MIT, Professor Wood held positions at NASA headquarters, NASA Goddard Space Flight Center, Aerospace Confederation, Johns Hopkins University, and the United Nations Office of Outer Space Affairs. Welcome.
Welcome, everyone. I'm so pleased to see you. Welcome to this very special plenary event. Welcome to everyone who's still coming in. Please come toward the front and find a great seat where you can support our excellent speakers. There is nowhere else on Earth that I'd rather be right now than sitting with our 5 distinguished panelists. One of the reasons is that we're celebrating so many years of the Next Generation Plenary at the annual International Astronautical Congress. In 2009, I was attending my second IAC in Daejeon, Korea. And I was honored to be in the first edition of the Next Generation Plenary. At the time, I was a doctoral student struggling to find my way, exploring what it meant to study the experiences of space nations, especially in Latin America, Africa, and Asia, and what it meant to bring that into a doctoral research setting. I gave some of my early ideas as part of the conversation in the 2009 Next Generation Plenary. I was so moved and encouraged. Right after the event, one of the leaders of the Brazilian space program walked up to me and congratulated me on giving relevant discussions on the policies facing his country. And I felt maybe I was going in the right direction for my research. So today, I think you can also provide wonderful support, feedback and encouragement to our wonderful students and young professionals, I want to ask a favor of all of you in the audience. Can you all get ready? I want to ask you to welcome again our great speakers with a very loud cheer. I'm going to say, ready, set, go. I want you to give them a very enthusiastic cheer. Ready? Ready, set, go. That is beautiful. Thank you for that energy. That was all for you all. So we're going to have a great time up here. So happy to welcome our speakers. And just so you all know, we really appreciate the long effort that many volunteers and people who are applying put in to make this a high-quality event. We've had months of practices and comparing notes and preparation, and you'll see that today. So a bit of logistics to remind us. We are using the Slido platform along with the other plenary leaders, and you can go to slido.com and just put in IAC 2022. You can also use the QR code that's being shown on the screen. And we encourage you to prepare your questions for our speakers. Each one will give a 3-minute introduction to their work, and I'll have a few questions as the moderator to start. Later on, I'll come back to your questions on Slido, so please give us some interesting questions, and I'll take some of the key themes and bring that back to our speakers. Wonderful. With that introduction out of the way, let's get to the real fun part of today's event. I'd like to introduce our first speaker, which will be Luke Heffernan. Please give us an introduction to your work. Let's welcome Luke.
Sorry, there we go. Thank you, Danielle, and thank you for everyone who's made it here today. I'm incredibly honored to be up here on stage with my wonderful co-panelists. It's amazing to be here in Paris today. I'm Luke Heffernan, and I've traveled a long way across the oceans to get here from Australia. Back home, my career has spanned from laser physics to founding or co-founding 4 companies, many I'm still active in, and one that is now a national scale charity. I've also recently been involved in the National Space Society of Australia's New Horizons Summit, co-chairing the summit to paint a new supply chain for sustainable lunar habitation and eventually Martian colonization. As we will hear in today's discussions, the first generations of off-Earth inhabitants and workforce will not be human. They'll be made of space-hardened gears, alloys, and chips. The generation after that may be the same, and maybe even the one after that. But eventually, our humans will join them out there, and we will no longer have the luxury of the worst-case scenario only costing time and money. If we want to protect the bravest of us, those astronauts who are going further from home than any of us have ever dreamed, we need intelligent and adaptive, non-human collaborators. But to expect that robots can be so thoroughly coded to dynamically collaborate with humans robustly in any situation where we might find ourselves would only be fooling ourselves, especially as missions become less predictable and further from Earth. As in other areas of our modern world, the benefits of harnessing the power of AI is undeniable, especially when considering various forms of deep learning and other types of machine learning and computer vision. Human-robot interaction, empowered by recent developments in reinforcement learning, has shown promising results in enabling this highly effective collaboration between robots and humans. Every day, AI gets a step closer to closing the gap and breaking through the noise in its training data, much like humans might take pragmatic steps and jumps into the unknown when we're not quite sure where to go next. We view today's robots as computers. To reach our goals in exploring this universe, we need to get them to the point of being our collaborators, our carers, and our co-pilots on this cosmic trip. Thank you, everyone.
Thank you so much, Luke, for helping us set the stage for our discussion on AI applications in space, starting with examples from the moon. Next, I'd like to invite Audrey Brecan to please continue our discussion and give us another application of AI in space.
Hi everyone, my name is Audrey Bercan and I'm a space system engineer who turned to the dark side and joined the field of computer science and AI a couple of years ago. At the start of my career, I was involved in the early design phases of Earth observation missions. And as an engineer, I quickly realized that you are often drowning in documents. What is the flight heritage of my mission? What is my payload accuracy requirements again? These are the type of questions that engineers may be asking themselves while designing missions, questions that will require them to go digging in documents and therefore losing a bit of time. And it is a vicious cycle, as the more missions we develop, the more documents we generate. Now, I know some people here are going to tell me that MBSE, Model-Based System Engineering, is going to save us all. And maybe, but it does not change the fact that we have accumulated a huge amount of documents, of text, that is today just asking to be mined and better structured. At engineering school, I had a very wise professor tell me that the best engineers are the lazy ones. So to become a better engineer myself, I started to look into a branch of AI called Natural Language Processing, NLP. So what is NLP? NLP encompasses all of the methods and algorithms that enables computer to understand human language. You are already using it in your daily life when you are keeping spams out of your mailbox, when you're chatting with a bot, or auto-completing your emails. As an engineer, NLP can help you better organize your requirements, trace them, check their qualities, or even compare them to your spacecraft architecture. Question answering system can go through thousands of documents in a matter of seconds and provide you with the exact information that you're looking for. So this is what I did during my PhD. I adapted a few NLP methods to the field of space mission design, leading, for instance, to the development of Space LDA and of the Space Transformer family, the first models, language models for space systems. The PhD was a nice warm-up, and now as a research fellow at the European Space Agency, I'm continuing my research, combining NLP with knowledge graph. Knowledge graph are a graph database with a semantic layer. What I aim to achieve is to go from data, which is unstructured, stored in various formats in various databases, and to go to a unified and structured view of a space ecosystem. To do so, I'm currently using a language model like GPT-3 to mine key information from text and to migrate it to a knowledge graph. And this knowledge graph provides us with a unified view of a space ecosystem, both from a technical and a business point of view. I strongly believe that NLP and knowledge graph can be key enablers for the space field, that they can provide a practical support both to experts and to decision makers beyond, well, throughout and beyond the mission life cycle. I look forward to the discussion with my fellow panel members, as well with anyone in the audience who might be interested in these methods. To summarize, let's be lazy together and let AI do the boring task for us. Thank you.
Thank you so much. You've highlighted that actually during the design process, we can already bring artificial intelligence as one of our tools to make the design experience both more meaningful and more efficient for designers. Wonderful. Thank you so much. And we'll next invite Antonio Stark, who's going to take us to another application of artificial intelligence in space. Welcome.
Hello, everyone. I'm Antonio Stark, coming in from Seoul, South Korea. It's so amazing to be here in Paris with so many familiar faces around. I remember being blown away at my first IAC, which was in Bremen a few years ago, and I'm so honored to have been given this opportunity to be on this side of the stage here today, thanks to the organizers of the Next Generation Plenary program. I hope that I will see some of you on this stage in the near future as well. While I'm involved in many different space organizations, I'm here at the stage today thanks to the hard work of all the engineers at the Unmanned Exploration Laboratory, or UEL. At UEL, we develop robotic systems for the moon and beyond, including 10 different types of rovers for the moon, and one of the first prototypes of the Ingenuity Mars copter that was flight tested in the Australian desert. We are living in an exciting age for lunar exploration, where the Artemis program is aiming to bring the first woman and the next man to the moon to stay. No human habitat in space can be constructed without robotic systems. We envision a future where up to 10 astronauts will be living on the lunar surface equipped with life support systems, rocket landing and launch pads, and communication arrays. While many people think that the hardest problem to solve on the moon for robotic lunar missions will be hardware, software poses as significant as a problem when in an environment as new and harsh as the moon. Let me give you two notable examples of how AI can be used to support a sustainable crewed presence on the moon. The first example is lunar construction. Construction rovers will operate in fleets, employing 3 to 4 different types of rovers and numbering in the dozens of units interconnected via orbital and local communication links with just a single hub to recharge power and deposit materials. While fleet system management is relatively easy when there are GPS, plenty of power supply, and operating in a known environment, the problem becomes harder by degrees of magnitude when you are trying to operate these type of systems when you have sparse communications, navigation, and power systems on site as the moon. This means we need to develop algorithms to dynamically assign the rovers to different sites and different tasks, all considering mission weight, comm relay windows, and existing lunar maps. The second problem that we are tackling with AI is autonomous navigation exclusively for the lunar environment. Gravitational difference, as well as the super soft regolith, means we have totally different traction factors for driving on the moon. As there's no ambient light on the moon because there's lack of atmosphere on the moon, normal vision leaves a lot of blind spots when there is no sunlight. We need to develop new algorithms that can use both LiDAR and radar navigation for short distance obstacle avoidance and visible light spectrum for long-distance path programming. We're literally rewriting an entire library on how to drive blindly, and we still have so many challenges we are left to tackle. These are just two of the most prominent problems that we're tackling right now, but we're also using AI for communication redundancy, data subdivision, and position and calibration. All these technologies are being developed with partners both domestic and international, and I'm so thankful that so many of them are represented here at IAC today. Our goal is to nurture an AI-driven environment in space that can act as an equalizer across sectors and nations. AI can catapult emerging nations to reach for the moon and smaller companies to participate in the cislunar economy. I believe that AI will be a driving force for sustainability in the new space sector, and I'm so excited to be sharing this future with you here today. Thank you so much.
Thank you so much for giving us some examples of some of the use cases where, in particular, a robot needs to navigate a unique situation that may have examples both in space but also on Earth. We'll ask about that later. Wonderful. I'm so happy to introduce Kelsey Dirksen. And as you speak, we look forward to hearing what some of the challenges are with uncertainty quantification. So please share that with us. Let's welcome Kelsey.
All right. Good afternoon, everyone. My name is Kelsey Dirksen. I'm a PhD student at the University of Oxford studying autonomous intelligent machines and systems, and I'm an incoming visiting researcher at the NASA Jet Propulsion Lab. I spent the last 2 years working as a satellite operator within the Earth observation sector, where I began to truly understand how impactful space technology is on our planet. I've been an active member of the space industry since 2018, where I've worked on machine learning projects, including the development of algorithms to assist with autonomous rover operations for NASA, space weather prediction at the Paris Observatory, and assisting satellite operations for the world's largest Earth observation satellite constellation at Planet. I'm also an advocate for creating an equitable, diverse, and inclusive STEM community at Oxford and across Canada as an executive member of the Oxford Women in Computer Science Society and mentor for the Zenith Canada Pathways Foundation. I like to consider myself as more of a jack of all trades when it comes to research focus, going against the grain of hyper-specializing in my PhD to a more broad focus of AI to enable space and climate science. Audrey already mentioned this. There's a lot of documentation that goes into space missions, and 2.5 quintillion bytes of data is generated daily. So that's 2.5 with 18 zeros after it. an amount of information that simply isn't feasible to manually process. AI can help us extract meaningful information from enormous data sets. And in utilizing AI in space, I've been working on research ranging from space-based data sets for tackling climate change disaster mitigations on Earth to understanding the formation of our universe. On Earth-based applications, I've been developing a deep learning model using space and remote sensing data to predict landslides in the region of Nepal. This is particularly challenging due to the lack of high-resolution data in the region and the complex nature of landslide events. Through deep learning and Earth observation, we can gain a deeper understanding of the covariates that trigger landslides to reduce the loss of life and damage to infrastructure from these events. Now looking outwards towards deep space, another pillar of my research that Danielle mentioned is known as uncertainty quantification. When developing a deep learning model, we're creating a mathematical model to represent a physical system. Essentially, we're using math to reveal information about a data set. At NASA, using the Cosmic Microwave Background, or CMB data from ESA's Planck mission, the goal is to utilize deep learning to separate the dust and other galactic emissions from the foreground to create maps of this CMB signal, and further provide uncertainty estimates of these maps that will represent our confidence of the true prediction of the signal. So ultimately, we're interested in studying the formation of the universe and using AI to do it. I'm thrilled to be here and honored to join my fellow panelists, and I can't wait to hear the discussion moving forward. Thank you.
Thank you, Kelsey. We already see this nice combination where you compare Earth-based examples with space-based examples, but you also highlight one of the metrics we have to bring into discussing AI. How do we talk about and communicate uncertainty? So thank you for that. Wonderful. We're going to invite Serena Lupu to continue, and please share your research with us as well. Let's welcome Serena.
Thank you, Danielle, and all the other panelists for their beautiful introductions. My name is Serena, and I'm a fourth-year PhD student in the Aerospace Robotics and Controls Lab at Caltech, and I'm very excited to be here with you today, talking about some of the topics I love most: space, robotics, and artificial intelligence. Let's briefly imagine how space will look like in 5 to 10 years. It's going to become very inexpensive to send a robot to the moon or Mars in the future. With launches happening frequently, maybe anyone from the audience could send a robot to the moon and Mars. But in order for those robots to do anything meaningful up there, they need to be intelligent. And currently, operating a spacecraft or rover in space requires a large team of scientists and engineers to develop sequences of commands to control the rovers or the spacecraft. Therefore, adding an autonomy capability on board will dramatically decrease the cost of the mission and also increase the science output. At California Institute of Technology, in my lab, the Aerospace Robotics and Control Lab, we aim to make robots think on their own. We not only develop the autonomy algorithms to give intelligence to these robots, but we also test them in our state-of-the-art spacecraft robotics simulator that you see here behind me. And when we are ready, we partner with industry like NASA Jet Propulsion Laboratory and the Aerospace Corporation to fly our mission to space. This is how the Castor mission started, which is a multi-spacecraft autonomy demonstrator capable of showcasing some of the most advanced autonomy algorithms for guidance, navigation, and control. For my PhD, I develop autonomy algorithms that combine machine learning methods with classical control in order to make robots achieve capabilities that were not possible before. Specifically, I develop model-based reinforcement learning algorithms with uncertainty quantification in the dynamics of the spacecraft or rover in order to develop exploratory controllers. One application of my work would be rovers trying to traverse complicated terrains on Mars. I'm very excited to be able to push the boundaries of autonomy for space at Caltech and also be here with you today, together with my panelists, trying to inspire the next generation of engineers to study space robotics and autonomy. I would like to sum up by reminding everyone that recently, James Webb Telescope showed us a small slice of the universe in very much detail. So just imagine how amazing it could be if actual robots could go there and explore those distant worlds. Therefore, I would like to invite you all to build this future together. Thank you.
Wonderful. Thank you all so much for giving us this introduction. We heard examples of using AI as part of the training and programming of robots, helping to think about operations on surfaces like the Moon and Mars. We heard example of wading through large amounts of scientific data. We heard examples of helping designers as they're working through the large amounts of data created in planning a mission. So thank you for these diverse examples. I'm going to take a few minutes to ask questions prepared with the panelists. And thank you to everyone. I see people are using the Slido. That's at IAC 2022 on Slido. Please feel free to add more questions. We'll come to those very soon. To get us started, I'd love to ask Serena, who just spoke, to help us with the first question. Now, you've highlighted examples of technologies, and all of us gave a few. What are some examples of AI technologies that were first used on Earth for benefit to society that you think could also be used in space?
Yeah, excellent question. Thank you so much. So on Earth, AI is present in autonomous self-driving cars, intelligent vacuum cleaners, exploration robots. And these technologies can be directly transferable to space because a spacecraft and a rover is just a robot with computation capability, cameras, etc. However, when we fly this technologies in space, we need to be careful. We need to test them extensively and really understand how and when they fail, because we can't just go quickly up there, fix it, and then go back.
Thank you for highlighting that there's many familiar examples. We may not notice the AI, but they're underlying experiences we have in our daily life. Let's go then to Antonio. What is your motivation for using artificial intelligence in the space sector?
So before I came into the space sector, and especially using AI, I was involved in the sector of sustainability. And after I majored AI during my university years, I realized the potential that AI can have in being, as I said in my speech, the equalizer across sectors. AI can make spacecraft and space missions much cheaper and easier because you can have different people collaborating in the same project as once. You're not exclusively relying on astronauts to be conducting the same mission. You're relying on a team of engineers to develop the set of algorithms to execute a mission, and you're learning all that, and you're taking it to the next version, the next iteration of the program, etc., instead of having to train a whole new set of astronauts that may take decades in the year. So coming in from the sustainability sector, I simply saw how much AI can play as a leveling field for new companies and smaller countries to participate in the space sector, especially to the Moon and Mars and beyond. And that was my very strong motivation for being here in this place.
Your answer is actually responding to some of the questions I already see coming in on Slido, so that's a nice place to go. My next question is for Luke. People often discuss a debate as if we have to choose between focusing more on human-based exploration versus robotic. What are some of the arguments in your work for combining human and robotic exploration?
Thank you. That's a big question, and of course subjective. So if anyone has any other opinions, feel free to jump in. My opinions on this start with looking at our options. We can use fully human exploration. Only people that are up on the Moon or in Mars or further get to help out there. We can communicate from a long distance using humans, or collaborate with robots in location. Of course, the one you'd want to choose may be based on the task. Transportation and medical situations might need a much faster response than something than particular scientific tasks. But in a lot of cases, the situation, like in a lot of machine learning cases right now, we are showing that there are machine learning algorithms that can outperform humans in many different areas. Why would we not have them there doing their best, avoiding emotion, helping us speed up our exploration and our response times when we have those available to us? We have the computation, we have the technology. Let's go with it.
Thank you, Luke. I want to return back to Audrey and talk about this topic of what it means to advocate for the use of artificial intelligence in the design aspects of a space mission. And what do you expect to be a future relationship between humans and computers or artificial intelligence in the design phase of a space mission?
Sure. So I think the first thing to say is that we're not aiming here to replace the human designer. So the idea is really to support the humans designing missions, to help them win time, basically, so they have more time to do more interesting tasks, I guess. And for instance, well, at ESA, one of the objectives is to improve by 30% the development time for spacecraft. And I think we really need to use NLP, use AI to achieve this goal. Also part of a more global, let's say, digitalization effort. And we're already starting to go in that direction. So we have a few activities that we have launched. So just to cite a few, we're developing a virtual assistant for feasibility studies done in a concurrent facility. To support experts navigating through their MBSE model. We also have a knowledge management team actually doing a knowledge graph, trying to put all of the ESA staff in a graph to combine, to link them to their skills or to their projects. Then we're using NLP to support the development of our ontology, the space system ontology, or to capture the knowledge of staff who are retiring. And finally, a bit more personally in my work, so as I say, I was using GPT-3 to mine key information in text like stakeholders, payload names, and to really organize it in a big knowledge graph. Yeah, and I mean, I'm just describing effort at ESA, but of course there are other agencies and industries also working on NLP.
So now you're bringing us to one of those moments in a conversation with artificial intelligence, and half the audience is asking, what does NLP stand for? So let's take a moment, because we want to communicate in a way that's good for everyone. Please give us a quick introduction to natural language processing.
Yeah, so natural language processing, NLP, is basically the field of AI which enables computers to understand human language. And that's not that easy because human language can be very complex. So for instance, if I say Danielle is on fire today, she's really rocking this panel, it doesn't mean that she's on fire, right? You know that as humans, but no, the computer doesn't.
Great example. Danielle's on fire today, and you all get what that means. That's excellent. Let me turn to Kelsey, who's also going to give us a quick tutorial. One of the things we hope to do is to make AI in space an accessible conversation. So please also further define what are the types of uncertainty we need to consider in discussing AI.
Yeah, thank you. The world's fastest tutorial on uncertainty quantification. So uncertainty quantification, it really boils down to knowing what we don't know, or providing some sort of confidence in our predictions from the output of an AI or machine learning algorithm. And this goes across kind of all facets of machine learning, from NLP to autonomous navigation, computer vision, all of these things. In particular, if we're thinking about space missions, Serena mentioned, we can't just go up to Mars or the moon really quickly and fix something, or if our rover gets stuck on Mars, these types of things, and it made that decision to do it using AI, that's not great. So what we're doing with uncertainty quantification, I guess, as an industry, is trying to provide some context into how confident we should be in what our model is telling us to do, whether that be a path planning algorithm or whether or not Danielle's on fire, these types of things. So that's kind of what uncertainty quantification is.
Thank you so much. And what are some of the particular reasons or opportunities to consider that, especially for space applications?
Yeah, in particular to space applications, there's so much data that we're gathering every single day. And in particular, if we're doing things related to kind of autonomous traversal and using sort of path planning algorithms, or trying to, collect Martian regolith, these types of things, and trying to do any sort of science analysis using AI, we want to make sure that we're confident in what the model is telling us or what our AI algorithm is telling us, because it's not very easy for us to go, back up out there and collect the information ourselves. So it's really important because space missions are very hard, they're very expensive. So if we're going to, implement AI on board things to make decisions for us, we better be confident that it's doing the correct thing.
This is wonderful. You're actually already addressing one of the top-rated questions on Slido, which we'll come back to. But let me invite Serena into the discussion, because you also think a lot about this in your work. Please go ahead.
Yeah, so with launches becoming more available and everyone could send robots to space, then the bottleneck is going to become operation. It's going to become operations. So you would rather accept a certain risk, but then you will decrease the operation costs. And from a research point of view, me and Kelsey are researching similar thing. She in the United Kingdom, me at Caltech on uncertainty quantification. So for example, what we do at Caltech, if we try to detect a solar panel, we don't let the AI algorithm just output, this is a solar panel. We have an uncertainty prediction. This is a solar panel, but we are only 10% confident or 90% confident. And then we can build up on that and improve the AI and make it robust for space.
Wonderful. Let me bring Luke into the conversation too. Both those on Slido and in our preparation, we were thinking about this question of how a robot working with an astronaut will create a relationship of trust. How can the astronaut feel confident in trusting the performance of that robot as a partner?
I do really like this question, actually. I was pondering it earlier today. And the hard part in this, for me, is that it's always going to have the human element. The initial stages, we start doing tests, we start showing the performance of the robot in particular situations, we move up the technological readiness levels, and we show it in action, right? Across that time, the humans start to learn to trust it. Across time, we become dependent on robots in a lot of ways. We all have our phones in our pockets, and imagine how hard today would have been without that. At that point of dependence, though, or that point of huge amount of trust, we start changing how we behave with the robots. We go away from some of the fallbacks we used to have before as well. There's a whole new paradigm we operate within. And then bringing new things into that situation or going back to the ways they were when we need those for safety become actually harder. And therefore, it's a whole cycle of changes in our psychology that are intrinsic in that trusting. Yeah.
This reminds me that in 2004, I used to be able to use a map to help myself drive somewhere, but today I have lost that skill set. Now I trust my phone to tell me where to go, and I'm not as good at map reading as I used to be. So, fair enough comparison. And let me turn to Antonio. Oh, please go ahead.
Maybe if I can just add
Definitely.
something also in terms of, I think, uncertainty and reliability. Sorry. So also in the NLP field at the moment where we have these very large language models, probably you've seen some very impressive applications of GPT-3 just writing a full article and it looks like it's been written by a human. But actually from my own experience, I think we still need also the human in the loop very often to double check what your model generation algorithm is providing you. So I've had the case where I had to face a few so-called hallucinations of the model. So the model, meaning my model was hallucinating, meaning it was kind of answering my question correctly in a semantic kind of form. So I would ask a launch date and it would give me a date. So that looks correct, but actually it's completely fake. So it's a bit as if you had a child kind of doesn't want to say that he or she is wrong and just is outputting something. So I think this also brings us to also the theme of explainability, AI, XI, which maybe we are all concerned by, which is also having your algorithm explain their output. So it's just not a black box, it's understanding why the algorithm is giving you this output. And with XI comes kind of accountability, so you can better understand the output of your model.
That's great. I have particular questions for Kelsey and for Antonio, but Antonio, you go first. You ready? All right. I thought you were grabbing the mic to make an addition. For Kelsey, I wanted to ask, take all this discussion on the trustworthiness and the sort of system-level behavior into the context of satellite constellations. A lot of interesting debates are happening on the role of using autonomy to do orbit changes, for example, or orbit management for constellations. I think you have some thoughts on the opportunities and challenges there.
Yeah, definitely. So when I was a satellite operator for the past couple of years, we started to implement a little bit of machine learning and using AI to help us make decisions, but we weren't necessarily using AI to, change orbit trajectory or, this is when you should take a picture or things like this, at least from my side of the operations. So I think it really comes down to risk versus reward, something that you were mentioning too, Serena, in terms of the risk we're willing to take, in terms of, how expensive is this satellite? If your constellation is 4 satellites, maybe you're a bit more concerned than if your constellation is 200 satellites, and one of the CubeSats, if for example is out of commission for a few hours, that might not be a mission-ending situation, but for cases when you have a lot smaller of a constellation size and a lot more expensive of a satellite, this is when you kind of need to consider, do we want to use AI to be actively making decisions, or do we want to be using AI to help inform decisions that operators should make, whether that be debugging the satellites or changing orbit trajectories or things like this?
Very helpful. Please go ahead.
Just a follow-up on that. Actually, we at Caltech, we develop a mission that consists of 3 spacecraft, and we try to do a docking eventually. So for docking, AI is very important because in case the docking fails, then you want to reconfigure and try again. And docking happens very fast, so you can't just send commands constantly. So you need to recompute the trajectory all the time using artificial intelligence.
That's very helpful, and I wanted to ask Antonio also to address this in the context of the unique challenges of the lunar environment. And of course, if you'd like to comment, Luke, on that as well. Go ahead, Antonio.
Absolutely. So my previous panel has given great examples, especially in terms of timing. In technical jargon, it's simply called latency, or sometimes latency in terms of signal or fidelity, and when we're looking at the data in general and how much fidelity the data can have to the actual environment. And those 2 things are very important because humans can't always be there to process this data and make the decisions. My other field of proficiency is actually the law and policy. And as Serena has already mentioned, the use of AI is a very high reward and high risk. Sometimes it can be used to supplement or support decision making, but other times it can also make the decisions themselves because of the amount of latency or the lack of fidelity that is available for a crewed mission or for people back on the ground. In those times, you kind of need to look at how much responsibility or liability can an algorithm or can this program can take, and see for the moon, a lot of these decisions that are life-threatening will still be made by human operators, even if there is high reward, because of some categories of risk, which we call catastrophic risks, are present. And when life support systems are present, you do need that liability to be traced back to a human operator just for later purposes and for more policy networks. But for the moon, especially for uncrewed missions such as rovers being used for constructing habitats on the moon, they can be very much supplemented by AI to provide on-site decision-making systems because the rewards are so high and the categories of risk that we're looking at are not catastrophic or usually in most senses.
Very important to bring in these aspects of both the technical, policy, and legal, and of course economic aspects. Anything anyone wants to add before we go on? I have a question I'm preparing from the Slido, but please go ahead.
Excellent. I was going to say, very comprehensive. Great work, Antonio. I would also like to look at, there are intrinsic complications with using just electronics in space in general. Space weather effects, dust, all those kind of things, as Antonio mentioned. So that all of those need to be brought into the larger holistic picture of using AI in space as well, especially on the lunar surface. Bit flips and so on like that in electronics. In this conversation, usually we just focus on the machine learning in an isolated sense. Can we trust its reason? Can we trust its logic? When it's tested in a lab, we are usually isolating the computer system itself in a server, something like that. We are in a very different environment up there. The whole system will operate quite differently, even if it is still processing in the same way. So, yeah.
Very important systems thinking to note that the software is now inside an embedded system that's inside a harsh environment, and that's going to add new behavior to the software. Well, we've had some good tutorials, some good explanations. All of you have contributed, and I so appreciate those who have been upvoting. So we have a clear winner on the upvoting on the Slido, and I hope you all will consider this question. So I'll say it slowly so you have time to think. In what respects might artificial intelligence be overused in a space context? We've heard examples for robotics, for orbital constellation management, for data analysis, and for design. So please think about your own areas. Where is there a temptation to overuse AI? Please go ahead if you're ready, Audrey. I'll ask you all to comment.
I think the first thing I could say is that maybe the risk of like using an AI to always mine data in a in past spacecraft architecture might actually at some point prevent innovation, I would say. So maybe we have to be careful that we don't keep redoing the same spacecraft if you were going to use a virtual assistant that just looks at past design. First thing I can.
If we ask the computers what has been built in the past and what's been successful, they will happily average that for us and give it back to us.
Also, there is a branch of generative design, so maybe you have to take that into account. Yes, that would maybe add the, let's say, innovation aspect to it.
And do you see a way in your work to help safeguard against just repeating the old designs, but to bring maybe some random innovation using the AI?
Yeah, well, apart from using a generative algorithm, that's where also the human can come in the loop. So even though we see artistic, let's say, AI like DALL-E that can produce images, I still think that in the future, jobs related to, let's say, innovation of artistic, of out-of-the-box thinking will stay more human-based, as well as empathy job, but maybe that's another discussion. But
we rely on the humans for art and empathy. Thank you. I glad that. Let's consider your other application areas. Where is there a tendency to overuse AI?
Sure, I can go ahead. I'll talk a little bit from kind of the Earth observation sector, and specifically I'm kind of focused on climate mitigation and disaster preparedness and these types of things. I guess this could be controversial, but we don't always need to use AI, and I think that sometimes it's actually not the best tool, and we kind of almost jump ahead to want to use it because it's a very fast-growing and exciting area. So maybe controversial to say on an AI4SPACE panel, but this is how I feel. I think it's really important to connect with your stakeholders that are using your AI solution. And this is sometimes where there can be a disconnect, I think, in terms of maybe, for example, flood mapping, or in my case, landslide prediction. You know, my stakeholders in Nepal, they don't really need a very complicated technical solution. Really, they need a binary map where I'm highlighted, this is where a landslide is likely to occur within the next period of time. This is where an area that probably won't have a landslide occur. And so sometimes if you have an AI pipeline or a machine learning pipeline, you know, fully end-to-end with all of these complicated things in this very complicated technical solution, the stakeholders that actually would be, you know, using this tool, they don't know how to do that. Also thinking about, you know, in terms of just access to internet or things like this. I'm from Canada. I've worked in, you know, really northern remote areas in Canada, and there's no cell phone service, there's no internet service, there's nothing. So how are they supposed to use my AI algorithm for flood mapping? It's just not realistic. So I think it's really important to think about who your solution is for and discuss with the stakeholders that are on the ground, that are using, hopefully, your solution, and what their needs are.
I absolutely love what Kelsey said. She's so right. So, sometimes AI is overused. For example, we at Caltech, we don't typically do end-to-end learning, which is like using AI for everything. We try to combine it with classical methods. And regarding going back to your question, if I make a parallel between Earth and space, I think when we are going to have highways on the moon and someone wants to do something malicious with the autonomous cars, then that's an example of an AI overuse, I think. It's very futuristic, but it might happen. I'm pretty sure we are going to have highways on the moon and Mars.
I also want to say that, love Kelsey's answer. We've all worked in machine learning for a while now, and we've all had the number, like everyone say that machine learning can solve everything. Every possible problem let's make a reinforcement model for this. Let's make a convolutional neural network, whatever it is. When most of the time, just understanding the user better is probably the first step you should be taking, rather than anything that's exciting. Yeah, like you said, they're probably not the thing you want to hear from an AI and space talk. But my answer to the overuse question, though, links to that excitement, I think, and the novelty of places we can apply it. But then I think I'd like to go down a more philosophical route as well, in that I think it could be overused in exploration, in using computer vision for rovers, and anywhere if we are building a habitat on the moon, that is inspiring. That's something we go, wow. Like, I've been thinking about that a lot lately. In the next 5 or 10 years, we could have people living on another planet. There's something you see in the sky every day, and there's people up there. We could very easily get tempted just to have better and better AI and just go do that, and we have robots up there. Like, cool, we've dug some stuff out of the ground, formed into a robot, and now that's up there. But that hasn't changed my mind about how I see myself. That hasn't given stories to tell our kids or brought us together as nations. I think that, so, yeah.
And then I would like to just give the last closing kind of answer to that. So I would like to answer this question a bit of a step backwards in my area of expertise, which is liability and sustainability, and because these are two ways in which we might overrate the amount of success an AI can take. We're very interested in AI. We're looking at AI being used in sci-fi movies, and we can say AI can do this, AI can do that. But a lot of times we're not looking at what will happen if the AI fails or if it makes a mistake. And those are systems that we are not adequately prepared for. In the sector of space policy and law, it goes back into the whole liability regime. And if there's a mistake that happens with an algorithm on the moon, how does that liability trace back? And lack of education as well as research in this sector is what makes sustainability or openness not a factor for exploration. Because currently, a lot of these algorithms and AI systems are being made by advanced countries, existing spacefaring nations. These data sets are trained for people who look in a certain way or for systems that operate in a certain way. And the good cases that they will fail if we have new types of astronauts living on the moon that are not traditionally from the spacefaring communities, or we are trying to employ systems or programs that were not developed in a traditional spacefaring manner. And if we try to use or employ AI without looking at these failed mechanisms and understanding that these mechanisms can fail simply because of the inherent biases, then I think that's where AI will be overused, because it's making space a more closed and gated community than the open community that we are really trying to use AI for.
Wise words from all of you. We have about 7 minutes left, and we're going to end right on time to make sure everyone can get to their next session. So I want to do a few rapid-fire questions where anyone can answer. We don't have to go through everyone. But these are the fun parts, building on the wise things you all just said. Questions around, what does the future look like? How do we make this more open, as you just said? So, number 1, what would you change about the space industry? Any topic you want. This can have to do with technology, human resources, policy. A few of you.
Well, I think the thing I would change, I would like everybody to give me their documents, okay? No, I mean the documents related to space mission design, because this is the first problem we have in NLP, and that I think you guys have, is access to data. So, yeah, so first of all, data is scattered, it's a bit everywhere, and then you have people that don't really want to share that data because of sometimes, let's say, some information, design information can be sensitive. So it's a bit counterproductive if every time we start a new NLP project, we have first to look for the data and label the data. So what I would really love to see is that our community of NLP in space gets together and start to provide large labeled data sets.
And I'll just go off again on the same sector, is when we talk about diversity, we talk about representation, but in AI, it's more about accessibility to different data sets, and that's what I think I would like to change so much about this community, because still this community comes with a lot of luggage and a lot of tradition and legacies. We don't want a situation where we have a community of astronauts on the moon village, and because someone said something in a different accent, or they made a command that was in a different language, we have a mistake because we don't have that language representation in the natural language processing library, or we don't have that relevant types of systems command in managing satellite orbits, and we have all the other countries or satellites are working fine, but these new entrant satellites, they change their orbits in a different manner and they deorbit very quickly. So representation and accessibility as an extension is one thing that I would very much like to change.
Go ahead. Okay. On my side, I am very passionate about democratizing access to space, specifically in the Earth observation sector. I think something I was learning when I was working over this summer on this landslide prediction in Nepal project is that there are a lot of open source data sets. I think NASA does a great job. Google Earth Engine, if any folks here have used that to extract, Earth observation data. These are great resources, but a lot of the focus ends up being on, the traditionally very large spacefaring nations, or, the United States, the UK. These types of countries have amazing data coverage. And then you look over, different regions of the world, and there's nothing there. There's no data there, or it's not accessible. And so, we all, I think, understand that the power of space and the power of Earth observation and what we can do with imagery and seeing change over time and these types of things. And I think we need to work harder on making this data accessible for communities that maybe not traditionally have, the GDP or the economic support to launch their own constellations. So that's something that I think I would like to see change in the future.
I'm passionate about this in terms of just general world change, but the space industry included, is probably education around AI. As we've been talking about, natural language programming, there are many tools there that help you synthesize, draft, proofread your work, or pull information out of larger data sets. There are computer vision models that let us shortcut or verify many other systems we have in place. Audrey mentioned GPT-3, amazing system out there right now by OpenAI. Since that came out, I've been using that to draft or outline many large documents or reports that I've had to do. Of course, not submitting them as they are, but get the bulk of the work out the way, or proofread, or check that it is matching the audience or the spec that was originally given. It's very easy to trail off into your own thoughts as you're writing. So it's, that's a few cents every time I use that, and it saves me hours. Imagine how much we could do if every single person in this room had an extra 3 hours in their day. So, yeah, I guess in the operational sense, we could get a lot more out of our days using these things as our collaborators, as mentioned before.
Yeah, if I would change something about space, I would love if robots could be developed faster for space. I absolutely love the Mars helicopter. It's my favorite mission because it's a small robot developed very quickly. I think JPL worked about 2-3 years on it, and it just worked so well. So I think we should have in the future more smaller missions like that and send them out in space frequently, because only like that we can really get science as fast as possible.
Well said. You all have brought some beautiful thoughts, and they really responded to many of the topics you and the audience gave us in the Slido. Questions around what it means for more countries and different types of groups to be involved with space. Questions about the need for education to help prepare our next generation to use these tools both on Earth and in space. Questions about the policy and law applications. Thank you all so much for the preparation, for the work you're doing in your jobs and your universities. Thank you to this wonderful audience and for the excitement you brought and for the key questions you asked. Let's close with a thunderous round of applause for this beautiful panel. Thank you so much. With that, it's my pleasure to close the 2022 Next Generation Plenary at IAC. Have a wonderful week, everyone. Thank you.